Yes, sir. I can hear you. Yes. Hello.
Okay, can you hear me, Srinidhi?
Yeah, yes, sir. I can
Okay,
hear you.
okay.
Yeah.
I had muted. That's the reason.
Ah,
Okay.
yeah. Okay. Sir.
I'll just wait for 2-3 minutes. Hey,
Oh,
you sent it on WhatsApp, right?
yeah. I sent it. Sir.
Uh, do you know whether people saw it or what?
No, like I think they know the classes, then they may join in 2 minutes.
Okay. I will wait. Yeah, I'll wait
Yeah.
for until I think 2-3 minutes. I'll wait.
Yeah, sure. Yeah.
Yeah, maybe instead of waiting, I'll just do a kind of a recap so that it'll help. It's useful and they can also see it later. So
Yes, sure.
okay, so recap. I mean, we did the. I think we did quantum entropy in two classes, right? So far. So
Yes, sir. Two
S of
classes.
rho. So we defined S of rho to be minus trace of rho log rho. Um, we showed a bunch of things. So S of rho is h of eigenvalues of rho. We showed that if rho AB is theta, then S of then each of any you take any cut, the entropies of the two cuts will be the same. We showed suppose okay have orthogonal support and P is a probability mass function, that is each term is greater than equal to 0 and they sum to 1, then S the entropy of the mixture with this convex with this distribution with this convex mixture with this convex distribution is first you tell me how many bits you need to tell me what is the index, and then with probability pk you have to give me s of OK number of bits. This is kind of the uncertainty. We last class I think we did this. I don't know whether we did this in last class or the previous class. So suppose pi 1 to pi l is a complete projective measurement, then the entropy of the outcome, if you don't tell me the outcome of the measurement, that is the entropy of the quantum state, suppose I do not know the outcome, I do not know the classical outcome, the entropy of the quantum state is more than the entropy of the original state. Um, so we did this. I stated this. I don't think I proved it completely. So so this is convexity. So we also did this. S of rho AB is greater than equal to S of is less than or equal to S of rho A plus S of rho B. This we kind of computed and left it at the last step. Um, we did this. We defined D of rho sigma to be minus trace of, not minus trace, plus trace of rho log rho minus rho log sigma. And the Klein's inequality tells us that the relative entropy is always non-negative. We use this in many of the proofs. Then we did this. So suppose so I will complete this proposition right now. Suppose I did most of it. I'll just recall and then do the last part. Suppose P is a PMF on the set, on the index set 1 to L, let's say, and rho L, for each index we have a quantum state for 1 to L. So what am I saying here? So I have a probability distribution on the index set 1 to L. And for each little L, I have a quantum state. Then the mixture, the entropy of the mixture is lower bounded. This is concavity, PLS of rho L, and is upper bounded by the same term with an addition of the Shannon entropy. This is what we almost proved, but we didn't. We almost proved it, but I'll just recall the steps and quickly go to the part I didn't do. So this is A and this is B. So proof. Just recall the first part. So proof of A. How do we do proof of A? We essentially define sigma AB to be PL. Let's say EL are orthonormal, EL tensor rho L. Okay. Now we know from the earlier, so we just use this inequality. S of rho A plus S of rho B is greater than or equal to S of rho AB. So if you just substitute for each of the terms, you will get A. One of the terms will get knocked off. That is the entropy, Shannon entropy will get knocked off. So that's proof of A. Proof of B. So proof of B. So what do we need to show? So I'll just kind of indicate this clearly. So we want to show that for any choice, for any rho L, 1LL, and PMFP, we want to show that the entropy of the mixture is dominated by the sum of the Shannon entropy of the PMF and the convex combination of the entropies. This is the goal, right? So first, so to prove this, we'll start with a simple case. So case, each of the quantum states are pure but not necessarily mutually orthogonal. Okay, XL hat not necessarily is not necessarily equal to delta LL. I'm just writing this is not necessarily equal. Okay, I'm not taking orthogonal states. I'm just taking pure states. So what do? We define this new, so in this case, what is the inequality that we need to show? So if this is the setup, right? What is the inequality we need to show? Let's look at the LHS. LHS is going to be S of summation PL XL. This is the LHS. And the RHS is, remember, so what is RHS? So RHS is H of P plus summation PL S of the pure state. But the entropy of the pure state is 0. So the RHS is just H of P. So really in this case, what we need to show is that summation PL XL is less than equal to H of P. This is what we need to show. See, this is not a trivial fact, okay? Remember, this is not a spectral decomposition. Remember, if XLs are all orthonormal, then there is equality. But generally, they are not. So in other words, if I take this state to be some new state, let's say a state gamma, then S of gamma will be the Shannon entropy of the eigenvalues of gamma, right? But that I have no idea how it is related to H of P. H of gamma, right? So I do not know how is that related to this. I don't know any kind of a relation. So this no relation known. So this inequality is non-trivial. Okay, so let's how do we prove it? So the way we prove it is as follows. So we cook up a pure state as follows. So we need it to be unit norm. So we define it to be what is this? XL, these are orthonormal. XLs are not orthonormal, but I'm going to put a tail to make it orthonormal. Okay, so EL hat is delta LL hat. Okay, so I define this. What do I know? So I'm going to call this sigma AB. So S of sigma AB is 0. So sigma AB is a pure state. So recall what we stated in the earlier part of the recap. So in this case, S of sigma A equal to S of sigma B. You take any cut, the entropies of the two parts of the cut are identical. So even if I take if I take a big state sigma A, let me call it gamma. A, B, C, D, E, suppose is is a pure state, then S of any cut. So if I take sigma A, gamma A, this is equal to S of B, C, D, E. The same proof goes through. Okay, so you can take any cut, and I'm just stating this as just as an extension of what we are doing. So this is these are identical. Okay, so just to keep this in mind. Okay, so coming back, so we have this, right? And our sigma AB is our quantity. So what is, sorry, this is not correct. I should not be calling this sigma AB. Sigma AB is the rank one, is the rank one operator corresponding to this density, pure state. Density operator corresponding to this pure state. Sorry. So sigma. Okay. So let's calculate what is sigma AB. What is sigma AB? Sigma AB is, I will just take L. Let's take R. So PL, PR root XL, XR, tensor, EL, ER, the E's are orthonormal. So what is sigma A? Sigma A, when you trace sigma A, you're going to get something like this. I'm not going to write this, but you can check this. XR, because when you have the inner product EL, ER, when you trace over partial trace over B, this is going to be delta LR. So one of the sums will squish out. But what is sigma B? Sigma B, you have to be careful. The excels are not orthonormal. So you are going to end up getting L R root PL PR. The outer product becomes an inner product. EL outer product EL ER. Okay. So this is your sigma A, this is your sigma B. So let us now, so what do we know? We know sigma AB is pure, I mean it's rank 1. So S of sigma A is S of summation PR XR XR. This is, recall, this is really, because our states are all pure, this is really what we are looking at. This is one term in the, this is actually what we are looking at, and we want to recall, we want to dominate this. So recall what we want. This is the bad thing about this online thing. We want to show the LHS is less than equal to RHS, right? So the LHS is this, right? LHS is this, and the RHS is this, right? So now we have got the LHS because sigma A is the so I'm getting I'm sorry about this. This has to be sigma A. Sigma A is your LHS, okay? And we know S of sigma A is equal to S of sigma B because sigma AB is pure. Now what do? We look at sigma B. Sigma B is this. Let us make a measurement. Recall one more thing that we recalled in this class is that if I have a, so let me go to that thing. So another thing we recalled in this class is this thing, right? So I'll use this. So if I have a complete orthonormal projection and I don't tell you the measurement outcome, the entropy of the post-quantum state is greater than equal to the entropy of the pre-measurement state. So we will use that and we'll cook up a measurement. So here I have sigma B and I want to somehow dominate this by something that will give me H of P, right? That's the goal. I have to somehow get H of P here. So what I'll do is I'll do a measurement on sigma B, and the most natural measurement you can think of that is complete and orthonormal, complete and projective. So recall this is your sigma B. I'm going to define my pi L, my measurement pi L to be EL EL. Okay. So what is pi L? Sigma B pi L. This is going to be just PL. Sorry for this notation. I could have used some J here so that it doesn't. You get a. Okay. So what is PJ? Pi J sigma B pi J. This is because you will have a EJ sitting here and an EJ sitting here. It will squish unless J equal to L equal to R. So you will end up having the square will become square. I mean PJ times PJ. So you're gonna have something like this. Remember XRs, they are all unit length. So you're gonna get something like this EJ. Okay. So summation pi j sigma b pi j is going to be summation pj outer product ej. So what do I have? S of sigma a equal to S of sigma b, but this is dominated by the entropy of the post measurement state. So this is pi j sigma b pi j, and hence if I so this left hand side is the left hand side, remember, is S of summation PL XL, and the right hand side is S of summation Pj, Ej, Ej, but this is a spectral decomposition of some state, and hence this is H of P. So I have ended up getting what I wanted. So what I've got is, if I go through this entire chain, right, what I get is S of summation PL. Instead of XL, I'm going to put it rho L, because I've chosen my rho L to be the pure states. So this is less than equal to H of P, but really there is a term here that is kind of zero, and that term is summation PL S of rho L. All this is because rho L is XL, right? So I've actually proved this inequality in the case when the states are pure. So B is proved when the rho L's are orthonormal. The rho L's, sorry, when not orthonormal. When the rho L's are pure, not necessarily orthonormal. I will pause for thoughts, questions, comments. Actually, what you should do is, if you understand, you should do that icon. What is that icon? There is this icon, right? Some reaction, yeah, some thumbs up hand is there, right? So I want to see everyone do that, so that I see that you understand. Okay, thank you. And the guys don't understand, I'm going to actually ping you and say, what's the problem? So you better let me know. Yeah. Okay, good. I see everybody do it. So I'll go ahead. Okay, next step. Next step is simple. It's just an extension of this. So general case. General case is actually simple. So so I have my rho L's to be some I'll write a spectral decomposition. Lambda LT. I will just call it YLT. Okay. And what do I need to show? I want to show this. This is what I want to show. Okay. Well, it's actually quite simple. What we'll do, let's look at this. Just think of this. Okay. So what is, so I'm going to create a new state. I'm going to create, let's say gamma LT, a new state. There's a new state. I define it as YLT, outer product YLT, and my distribution, now I'll call it P hat. P hat is this entire vector PL times lambda LT. See, I'm just the T can depend on the L. Okay, so it should be something like this DL, but it's okay. I'm going to just not make it more complicated than what it should be. So this is my vector. So now I'm just going to use case A for this ensemble. So what do I have if I use case A for this ensemble? S of, I have this PL lambda LT YLT YLT, this L and T, right? So I'm just kind of do the spectral decomposition and look at each one as a pure state, and then just kind of streamroll the previous group. So we know this. What is this? This is just H of, now the big vector P hat. This is simply coming from the case A. Agreed? Okay. Okay, now what do you do? So what is H of P? I will just show you that H of P is what we are looking at. H of P hat. Okay, sorry, H of P hat. So what is H of P hat? H of P hat is H of this big vector P L lambda LT, right? L 1 LL, 1 TDL, right? So let's just write this down and we will see what we want.
Sir,
Yeah, please.
can you please repeat the previous one? Like,
This one,
how
right?
did it come? Yeah, how
This
did it
one.
come?
Yeah,
Yes.
yeah. See, what did we do? If we take row L to be pure states, XL, and I have a vector P, right? Tell me if you agree with this. I'll just write this down. So if I have this, then I know this, right? I know this PL XL. This is less than equal to H of P. I know this. You agree with this?
Yes, sir. Yeah.
Okay. Now what I do, I am just looking at, so I now my row L's are not orthonormal. Okay. So let me use my row L's are not orthonormal. But what I do the spectral decomposition. And when now what I will do is I'll define a new vector P hat. My new vector P hat is what? It's a big vector PL times lambda LT. So 1 LL, 1 TDL. You see what I'm doing?
Yes.
So I define this huge big vector. See what is happening. There are multiple this YLTs, right? My rows were never, my proof worked for even non-orthonormal states. So now I'm going to just take this entire collection in the spectral decomposition. Each one has a rank one of, each one has a pure state with this distribution P hat. You agree?
Yes. Yeah.
So now I will just write this inequality itself. Now with respect to this P hat and this YLT states, that's all I'm doing here. So so I'm just writing exactly this inequality here, but for the vector P hat and the states lambda YLT. You understand?
Yes, sir. I got
That's
it.
all I'm doing. Okay. So now the right hand side is given by this, right? Because now my P hat is this. But this you can easily see. What is this? This is essentially the following, right? L T. PL lambda LT log 1 by PL lambda LT. But what I'll do is I will just instead of writing it like this, I'm going to instead of write, okay, so let me just do it. L T PL lambda L T log 1 by PL plus L T PL lambda LT log 1 by lambda LT. Okay. I just split the log. Okay. This, if I sum, remember what is this lambda LT? What are the lambda LTs? Lambda LTs are the spectral decomposition of the row L's, right? So suppose I do lambda LT, when I do the summation over T, I get 1. So here I get PL log 1 by PL because I can just sum over the T. The other terms don't depend on the T. If I sum over lambda LT over T, I get 1. Okay, so how the way you should see it is this guy is 1. The second term can be written as summation L PL T lambda LT log 1 by lambda LT. This is exactly what we want. This is the entropy of the vector P plus PL S of row L. Remember what is row L? Row L spectral decomposition is lambda LT ELT X. What was that? YLT, I think. YLT.
Sir, it is log 1 by lambda LT.
Yeah, lambda LT. Thank you. LT. Okay, correct, right?
Yes.
So this is it. So what did we get? So we the same inequality we used. So here on the left, what is the left hand side? The left hand side is indeed left hand side is indeed S of L T P L lambda L T Y L T Y L T. That is indeed S of summation P L rho L. So I have essentially shown that summation P L rho L is less than equal to H of P plus P L S of rho L. This is what we wanted. I will wait for you to say that you got it.
Sir, can you repeat the last line again?
Yeah, see the left hand side. See, you agreed with this, right? So let me use another color. 1 second. Okay. So you agreed with this step, right?
Oh, yes, sir, got it now. Yeah.
Yeah, that's it. So the left hand side is what we wanted. Left hand side is indeed what we wanted. That's what is here. That's what I've written here. The right hand side, I reinterpreted this big vector and saw that it is indeed this thing. Got it?
Yes, sir.
Okay. Niranjan, you got it? Hey, Niranjan, you got it? Okay, he seems to be doing something else. Okay, got it. Fine. Cool. That's that. So that's that. So the next proposition. Actually, I will not prove this, but okay. Departures. I'll just write this as departures from classical entropy. I'll just mention a few things. Okay. Recall in the classical world, right? We had similar things. So we had. I don't know whether you showed all this. Tell me which all you showed. We had this. So we have an analog of this even in the quantum world, right? The second thing, I don't know whether you showed this, but this can be shown. This is equal to h of x plus h of y given x. 3. So you can see that h of y. So if you combine these two, right, 1 and 2, you will see that h of y dominates h of x given h of y given x. Okay. There was another fourth thing you can show. I don't know whether we showed this. H of xy dominates h of x or h of y. Both. I'll just say h of x. You can always swap the two and you can say this. You can show this. You can actually show this just by the fact that you can just show this by the fact that h of y, the conditional entropy is positive, non-negative. You can show this, and hence you can show this using the second one. Okay, so you can show all of this in the classical. So you have a notion of h of so you have a notion of conditional entropy, right? Classical permits a notion of conditional entropy, and it has very good interpretation also. In the sense, I told you this. I didn't give you a proof, but I told you this, and some of you were slightly surprised. Remember that if Alice is observing X, so Alice is observing. So let's say Alice. Bob is observing Y. We know that if Alice also observes y, then she only needs to send h of x given y number of bits for Bob to recover x, right? For this guy to recover x, Alice only needs to send h of x given y number of bits. But what I told you is you can do this even if Alice doesn't know y, and that is the surprising thing. And so it gives a notion, or it gives some kind of a physical interpretation to the notion of conditional entropy. So h of x given y can be thought of as the amount of bits that an observer of y needs to be given to reconstruct x. So it has some interpretation, right? The question is, can we define a similar quantity in quantum? It turns out that's not easy. Okay. There have been multiple attempts. You can look at Wild, and Wild will do a discussion. But I will define a simple version of conditional entropy. I'll define a very simple version of conditional entropy. It's not it's useful to some extent, but not to a large extent. But it's actually useful to some extent. So I'm going to define that. Remember, in the classical case, how did we define h of x given y? We defined that as this py of y entropy of the distribution px given y, right? This is what we looked at. We looked at this distribution x given y when we fix y, and then we mix that with the distribution py, right? That's how we define h of x given y. We can't do that in the case of quantum because we don't have a notion of conditional distribution. Okay, so we are going to define conditional entropy as follows. Suppose so let me motivate it. So we know that in the classical world, right, h of x, y, I don't know whether you showed this, but you can go ahead and kind of show this, is the entropy of x plus the entropy of y given x. So you first tell me what is the uncertainty in x, and given the uncertainty in x, given x, what is the uncertainty in y? You can split your uncertainty in x, y as follows. So this tells us that h of y given x is h of xy minus h of x. So we're going to use this relation to define the conditional entropy in the case of a quantum setting. Okay, suppose sigma AB belongs to D of H1 tensor H2. The conditional von Neumann entropy of system B given system A. This has to be this is only a definition. Okay, so there is no sense of system B given system A in the case of quantum, but the quantities of use is S of, so the notation is slightly different. I mean, not really, but slightly. B, remember we used to write sigma here or rho here, right? We are now writing it as B. B given A with respect to the state sigma AB. This is how I write it. Okay. Remember we used to write sigma A like this or sigma rho AB. Now I'm writing conditional entropy. So I can't write sigma A given sigma B. This is how I write it. This is defined as S of the total quantum state, and you subtract out the given part. Okay, so this is the definition. So I'm kind of using this relationship in defining this. I'll make a couple of observations. Okay, first, okay, I needed to make one thing. I talked about the departures, but I didn't talk really about the departure. So observe one thing in the quantum. So suppose I should be, and I'm just going to pull this down a little bit because I want to state it here. Write something. Okay. So with regard to the fourth identity, right? So suppose I take a state theta AB. Theta AB is just some state. Some state. And theta A is, say, I trace over the B part of theta AB. Okay. Is this true? Is this always true? Always. Is this always true? The people who say yes can say thumbs up, and the people who say no can say thumbs up. Is there thumbs down? Yeah. No, there is no thumbs down. Okay, the people with yes can say put the green mark, and the people will say with red can put the red mark. Or okay, you can write in the chat. Not true. Is this always true? Because this is in some sense the equivalent of the fourth identity, right? Not always true. So this is indeed not true, not always true. That is because, remember, if I take my theta AB to be a pure state, right? We know that the parts have identical. So if I take this, so take a very simple case, right? Just take theta. Just take. I mean, this is very simple. Take u to be 1 by root 2, 0, 0 plus 1 by root 2, 1, 1. Right? And if you do theta AB to be UU, and theta A, you will end up getting 1 by 2, 0, 0 plus 1 by 2, 1, 1. You can show this is also theta B. So you will see that S of theta AB is 0. And we know that the parts are equal. And really, by this example, I'm showing that the parts have non-zero entropy. So this is 1. So clearly, this is not true, right? This is not necessarily true. Not necessary. When you interpret this correctly, it's not necessarily true. So that means that the whole may be less uncertain than the parts. Right? We saw, I mean, it makes sense because we saw that you can take a singular state, I mean, I'm using the word singular for a reason here. So you can take a pure state in two components, and you partial trace, you're going to get a mixed operator. So you take a pure state in two parts. Pure state means it has zero entropy. You partial trace it, you get a mixed density operator with a non-zero entropy. So clearly this is not true. And the first consequence, I mean, if you look at it, the consequence of this is that, so if you, I'm just going to write this in gray. The consequence of this is this can be 0, and this can be greater than equal to 0, which means that the conditional entropy can be 0, less than 0. Okay. So remember, one of the things I told you that the conditional entropy is non-negative, right? So this is not true in the quantum world. If something is true, and I will just state that and not prove it. So this is the definition of conditional entropy. It turns out, so you look at 1, 2, 3, 4, okay? Stare at 1, 2, 3, 4. One says one is subadditivity. That is, if I individually, if I add up the entropies, that is greater than the entropy of the joint system. The second states that the joint entropy can be written as the individual plus the conditional. The third one states that the uncertainty in Y, if I know X, is lesser than the uncertainty if I don't know X. So the left-hand side is the unconditional entropy of Y, and the right hand side is the conditional entropy of y. And what third one says is that knowing x reduces the uncertainty in y. Okay, so the way this is kind of written down, this is kind of, always remembered, is conditioning reduces entropy. That's the way it is remembered. Conditioning reduces entropy. Okay. And the fourth one says that a bigger system has more entropy than the smaller system. In quantum, one is true. Two is true by definition. Okay, because we define this quantity as the difference. Four is not true, and it turns out three is true. Our definition permits the the truth of three. Okay, so conditioning does reduce entropy. So I will just state that as a theorem, but I will not prove it. I'll prove it later. Okay. Conditioning reduces entropy. So S of B given A with respect to a state sigma AB is always lesser than equal to S of sigma B. Okay, so what do? You start with the state sigma AB, you define its partial trace sigma B, and then you look at S of and then you look at sigma AB minus S of sigma A. This is less than equal to S of sigma B. I think this is obvious, right? Now it's obvious. Actually, this is actually obvious by the, yeah, I thought my proof was more involved. This is actually obvious. Yeah, so this is actually proof. Proof is done. Proof is by subadditivity. Okay. I will just state one last proposition and then I will go to quantum typicality. This is actually a major theorem. It takes a lot of effort to prove, and we will do this at a later point when we really need it. Okay, and this is called strong subadditivity. There are many proofs of strong subadditivity. All of them are quite involved. I will state it and prove it later.
Just one question. So for the subadditivity, you use
noise. Okay, yeah.
So you just use the first property, right, to prove the third property.
Sorry.
So to prove that condition reduces entropy.
Wait. Let me reduce my volume. Your volume, your mic, I think, is too strong or something of that sort.
Oh, wait. Let me reduce my mic volume. Wait a minute.
Yeah.
Is it fine now?
It's okay. Don't go ahead. Let's work with it.
Oh, this. So did you use the first property to prove this, that conditioning reduces entropy?
Yeah, I used this. I used this property in proving this. I used. See, remember S of rho AB. We know this, right? S of rho AB is less than equal to S of rho A plus S of rho B. So if I write this correct, if I write it differently, I get S of rho AB minus S of rho A is less than equal to S of rho B. This is, sorry, less than equal to, this is the inequality. And I have defined this to be S of B given A, rho AB, right? So this is correct.
Okay, got it.
Yeah. Okay, I will write the strong subadditivity. I'll just write it, but I'll not prove it. Strong additivity says something like this. Suppose sigma A, B, C is a state. With three systems, A, B, and C. Then S of sigma AC plus S of sigma BC is greater than equal to S of sigma AB plus S of C. This is the stronger, sorry, sigma ABC plus S of sigma C. This is the strong additivity, strong subadditivity. And I will defer a proof. The proof actually comes from monotonicity of the quantum relative entropy. Okay, I will defer this and I'll do this later. I just want to get into, I don't want to keep doing, some inequalities with these quantum entropies, and then you'll wonder, okay, what's going on? We'll do something more physical. That's the reason I want to get ahead. So proof deferred. Okay, so let's go to quantum typical. Start in a new page. So we did a bunch of things with quantum. We introduced quantum entropy, proved some properties. There's some more, and I'll give some of them as exercises. Okay, I'll just pause for a minute. Okay, so recall. Just recall, what did we do with classical? The idea was the following, right? Recall. What the idea was, okay, suppose I have a set X. I have a distribution Px. I kind of looked at, I wanted to identify, I mean, at some broad level, what I wanted to do was to identify some subset T of Xn, right? And the exponential growth of this set, so I'm going to put T underscore n because it's not a Cartesian product. And somehow I wanted to look at the exponential growth of the set Tn should be somehow smaller than the exponential growth of the set Xn. And the probability that I will fall in the set Tn, I'm just going to write it like this, is very large. Right, so I have a big set Xn, and I want to find an exponentially small set where all the mass concentrates. Right, so I have a distribution Px on X, and I want to find an exponentially small set where all the mass concentrates. This was kind of the goal of our classical typicality. We will see kind of an analogous thing in quantum. Okay, so let's look at the following. So I have a state rho. Right. So always, the state kind of goes to the Hilbert space, and PMFs on X goes to kind of density operators on X, and you will see similar things, right? So okay. Now, what I want to do, let's say rho tensor n. And just like I took px tensor n, right? Px product px, I'm going to take rho tensor n. Now the question is, here what is happening? In some sense, what I'm asking here in the classical world is there a set on which the probability concentrates, right? And the set should be of exponentially small size, right? So in some sense, I can trap Pxn. I can trap Pxn inside this. I can pretty much tap Pxn inside the set, right? A similar kind of a statement goes into the quantum thing. So H is some space, right? H is some space of dimension H, let's say dimension D. Rho tensor n, where does this live? The dimension of rho tensor n, the space in which rho tensor n lives, you think at least it lives, is what?
D raised to n.
D raised to n, right? Just like cardinality of x raised to cardinality of x to the n, I get d tensor n, right? Now the question is, can I find a subspace? Okay, can I find a subspace T subspace? So I'll call it Tn, similar in that notation, such that the 1 by n log of the dimension of Tn. So I'm sorry, I should have used mod Tn here. And here also I should have used this mod. So that's why the mod becomes the dimension, right? Dimension of Tn is exponentially smaller than the dimension of H tensor n, right? I want something like this. And you know, what is the notion of I can trap pxn inside Tn, right? What is the notion of that? The notion of that is I can find if I do a projection, right? So suppose I do a projection. So I do a projection on Tn. Tn is a subspace, so I can define a projector on Tn, right? If I have a subspace, I can define a projector. If I do the projection, so think of the following. I'm thinking of a measurement. I'm thinking of a measurement, pi Tn and I tensor n minus pi Tn. Okay, please kind of just listen this. And if you don't understand, you should tell me and I will re-explain because this is important. So I'm looking at a measurement with two operators. So it's a projective measurement with two operators, pi Tn and I tensor n minus pi Tn. And when I look at the trace of pi Tn rho tensor n, this has to be very large. In other words, I have captured rho tensor n inside the subspace Tn. So I want these two properties, very similar properties to these two properties. So I'm going to call this 1 and 2, 1c and 2c. And here I have 1q and 2q. So in other words, this rho tensor n pretty much lives inside the subspace Tn. Though it is living in a dimension of size d10 d power n, it can actually be you know trapped inside a smaller subset, a smaller subspace. That subspace I have to identify. That's the goal. Okay. This is quantum typicality. The reason, see, it's like this, right? Let's go to the classical world. If you observe a large string generated by this distribution Px, that large string will most likely live inside this small blue set, right? It is most likely live in the small blue set. Similarly, in the quantum world, if you prepare rho tensor n, a big quantum, a big n particles with the same kind of preparation, you prepare n particles, maybe 1 million particles, and you put them together. If I make a measurement, so this is kind of a click or a no click, I am going to get my outcome most likely with regard to the click. This is the click and this is the no click. So I will most likely get that click. And well, I could have easily got that if I had chosen this to be I tensor n, if I just I tensor n and 0 tensor n. But I'm not looking at the entire subspace. Now I'm able to localize it. Okay, that is kind of quantum typicality. The goal is to find, so the goal of quantum typicality in some sense is to find this Tn and define this pi Tn and prove properties similar of this kind. Okay, so we will do that. I will just pause for thoughts, questions, or things you don't understand. So throughout we have seen this, right? Set becomes subspaces. and then so essentially we are now looking at subspaces, and size of sets becomes dimensions. So it's kind of analogous. You will see this analogous kind of relation go through. So I will define. I'll leave some things for you to prove. So I'll define the notion of a typical subspace. Remember, we defined the notion of a typical subset, and then we prove some properties of that. Exactly similar to that, I'll do some things here. So suppose a density operator has a spectral decomposition rho. Okay, so generally I'm going to also kind of, generally how do? We generally write it like this, right? We write lambda k, ek, something like this we write, right? I'm going to, instead of this, I'm going to write it like this. These are non-negative that sum to identity. The lambda k's are non-negative that sum to identity. So I will just call it px, p of x, px of x, just for, don't worry about it. Just call it this way so that it makes life simple. And I'm going to call this ex. You don't have to worry, because if this was something like lambda 1 e1 to say lambda d ed, you can just let your x to be 1 to d, and it's essentially the same. Lambda I becomes px of I. That's all. There's no big deal. And I'm just changing the index to x. Yes, it might seem a little weird, but it'll help. I'll just gray all of this out. Okay, has a spectral decomposition. We let the delta typical subspace of rho be defined as T. This notation is, delta. It's sitting within an n-dimensional space, and it corresponds to the density operator rho. This is defined as the span. Now, what I do exactly what you think I should do. EX1 tensor EXN. Okay, I take all those such that this vector x1 through xn, right? This is in the typical, the previously defined typical set of the distribution Px. Okay, I'll give you an example because it might be slightly hard to understand this. I will give you an example, but just hold on. And I'm going to add the typical projector. I'll say the delta. Okay, so I will say the delta typical projector of rho as pi. So this, this notation we're going to get success. I mean, over time we're going to get more and more lazy, and we're going to remove some of these subscripts and superscripts. But for now, we'll write it like this. This is essentially just the projection on the t delta n, but I'm going to write it down explicitly. So that is ex1 all the way until exn. ex1 outer product, the rank one, the sum of the rank one projectors, where indicator functions. I'm going to include all, I'm put all the xn's inside my t delta n px. This is the classical t delta n px. This is my typical projector. So I will explain this because this whole thing might seem a little bit involved. So with an example. So let's do an example. let me do an example. So, so row, let's say, is the following. So 3 by 4, E1, E1. I'll tell you what each one is. 1 by 8, E2, E2. Let me do 1 by 16 plus 3 by 16. E3, E3. Okay, what is E1? E1 is the vector 1, 0, 0. E2 is the vector 0. If you want, I can write I0. And E3 is the vector 0, 0, 1. So they are orthonormal. The rank, it's a spectral decomposition, and I have this. Okay, so I'll tell you how I am doing this. So, so look at E I1 tensor E I2 tensor E I3 all the way until E IN. So, right, each of the I1, I2, I3 to IN, these all live inside 1, 2, and 3. But the number of I1s, so the number of ones in the vector I, so this is the vector I, right? This is vector all indices, right? The number of ones in the vector I, that ratio has to be close to 3 by 4. So delta times 3 by 4 by log cardinality, that is log 3. And number of 2's in the vector I has to be also close to 1 by 16. Delta into 1 by 16 divided by log 3. And the number of 3's in my vector I by n minus 1 by 3 by 16 has to be less than delta times 3 by 16 by log 3. So you understand what I'm doing. I'm taking all these tensor products. I'm taking a tensor product. If the number of ones is close to 3 by 4, the fraction of the ones, the fraction of 2's is close to 1 by 16, and the fraction of 3's is close to 3 by 16. So, for example, suppose I take n to be 16. Let's take n to be 32. Let's take n to be 32. Let's take delta to be, say, half. Let's see what I get. So I'm looking at E I1 tensor E I2 tensor all the way until E I32, right? What should this vector I, this is the vector I1 to I32, right? The number of zeros in that vector, so let's see, number of ones in that vector divided by 32 minus 3 by 4 has to be at most, so delta I've taken to be half. So, okay, so 3 by 8 times log 3. So I don't know what this is. It looks like it has to be, what is 3 by 4 times 32? That's 8, 24. So it should be around 24. So there should be around 24 number of ones here in this thing. Number of ones inside the vector I, should be close to 24. Number of 2's in the vector I should be close to what? 1 by 16 times 32. 2. Correct? Yeah. Number of 3's in the vector I should be close to what?
6.
32, so 2, 6, 6. Yeah, they add up, right? So this may be, maybe you will get 23 to 25, maybe you'll get 1 to 3, maybe you'll get 5 to 7. Okay, that's so take all these vectors, look at the span of them. That will be a subspace, and you look at that subspace as the delta typical subspace of rho. And then what's your delta typical projector? It's just the projector on that subspace. That's your delta typical projector. Okay. So, so you see how strongly it relies on the classical notion of typicality, right? Because that vector is coming from there itself. Okay. First thing, there are some remarks which none of you asked so far, which I will state. Well, the question is this well defined? That itself is not clear because the spectral decomposition is not unique, right? So the question is this well defined? So I'll do the simple thing and I'll leave the bigger thing to you, Alex. It's not difficult really. One, if the eigenvalues are all unique, then it's well defined. There's no problem because if the eigenvalues are all unique, everything is unique. If all the eigenvalues are unique, that is, it's all the eigenvalues are unique, then it's actually very well defined. So well defined. If all eigenvalues are unique, are distinct. I should not use the word unique. Are distinct. Two, see, even if the eigenvalues are not distinct, right? This decomposition rho as summation lambda k pk, where pk is the projector on the subspace corresponding to identical eigenvalues, on that subspace corresponding to identical eigenvalues. This decomposition is unique, and you have to just work with this. Okay, so that's how you show. I'll just write it like this. Proof of general well-definedness is left as an exercise. Not difficult actually, but you have to use this idea. Proof of general well-definedness is exercise. Use uniqueness of use uniqueness of this in proving that. That's how I'll write it. Okay.
Just one question.
Yeah, please.
So in the point 2, your alphabet size would be k, right? Like the distribution would be on k things when you define the typical set. Okay.
No. What is k? Where is k?
So you have indexed it from 1 to k when there is a non-unique eigenvalues. No, if you go below, like the last point. Yeah, this one. So at capital K.
No, even in this case, you will look at the entire subspace. You will not see, this will still have some. Okay, so the point is this, right? This can be written as the following, right? K equal to 1 through K. J equal to 1 through dk, d little k, lambda k, ekj, let me use ukj, just for ukj, ukj. You can write it like this, right? See, what I'm saying is this summation in the subspace ukj, you can take a different set of eigenvectors. That's what I'm saying.
Oh, but the subscript would still be the same, right? Like even if the eigenvectors are different.
Now you will consider the entire your typicality will be defined on this d1 plus d2 to all the way dk. This will be your cardinality of x will be this, and you will see, because this is still a spectral decomposition. Okay, so this is still a spectral decomposition. So everything I said previously should work. So in other words, you what you do is you define it's like this, right? So I'm going to this can still be written as like this, right? I'm going to call it some gamma u fu. It's just that now u runs from 1 to d1 to all the way until dk. These FUs are the same as these UKJs, but UKJs are rotated within the subspaces. And now you just your typical subspace is going to be span of F I1 tensor all the way until FIN. So this vector IN, this is a vector sitting inside this thing, right? So I will write it like this: D1 dk to n. So what do I mean? Each term is within each element is within 1 to d1, d2 to dk. And if I take any element in this vector I, it has to be close to gamma A, delta gamma A by log d1 to dk. Do you understand it? It looks complicated, yes, but it's not really. All that I'm saying is, see, don't worry, just do a spectral decomposition. No matter what that spectral decomposition is, your typical subspace will be identical. That's all really I'm saying.
So in your distribution, you would just have the same probability values for a few of the terms in your universal set. Like that's the only difference, because some eigenvalues are the same. So there'll be something. There'll be many things in the set which have the same probability of happening. That is the only difference.
Let us do an example and then you will understand. Maybe what I'll do is I will cover an example and then you will understand. See, what is happening, Tejas, is that you just see when you have row with non-unique eigenvalues, right? The spectral decomposition is not unique. When the spectral take one spectral decomposition and you define the typical subspace according to that spectral decomposition, just as in here. So what you do, you just you just follow this. You don't worry. Throughout this definition, I never worried whether the lambda k's were identical or not, or the px's were identical or not. I never worried. I just gave this definition. You do the same thing. You take one spectral decomposition of rho and you do the same thing. You'll get a typical subspace. Okay. Tomorrow you wake up and you take another spectral decomposition and you write a different typical subspace. All that you have to show is these two typical subspaces are identical. Right?
Yeah, just as subspaces, correct.
Yeah, as subspaces, they're identical. And to do that, I'm telling you, go ahead and use this fact that this is unique. This decomposition is unique. So you aggregate those non-distinct eigenvalues, write it as a projector. Now use the fact that these are identical in the two subspaces, and then you have to show. So it's a little bit of work, but you can show. I mean, you can convince yourself first taking three-dimensional with two eigenvalues, and you can kind of show. Because see, what you are doing is you're taking all combinations and you are doing a subspace, right? So you'll end up actually collating all of them. You'll end up getting exactly the identical subspaces.
Yeah, I mean the basis would be different, but you will get the same subspace after the span is taken. That's
exactly.
What it is.
Exactly. That's the idea. Okay. Okay, so so I will just, I think I have finished 1 hour 20 minutes, right? Yeah, I started 1, so I started 5:30. Yeah, correct. So I will just what I will do is I will just state 3 things we did in the classical world, and then I will state the quantum analogs of it, and we will see that we will prove that. Okay, 1. What did we show? We showed that the probability that the guy belongs to the typical set is large. Then we showed that the typical set itself is not large. One minus epsilon times the same. I'm just not gonna write it because of the time constraint. This comes here. And the third one we observed is that for if xn belongs to t delta n px, then the value of that probability is sandwiched between exp. I'm just going to write a dot. Okay, I'm just going to write equal to with a dot because there is a minus and a plus. So exp minus n times h of px plus or minus delta. This is what we have, right? We have exactly the same things here. So remember, we have defined a projector, right? So the trace here, the fact that you will find the sequence of in that particular set, you'll wake up and you will see that sequence in that particular set is large. Similarly, the fact that you will get a click according to your typical projector delta n rho tensor n, this is large. Quite beautifully, this also is true. It is not difficult. I mean, it literally follows, the proofs just simply follow from the classical world. You can actually see it. That if I look at the dimension of this typical set, typical subspace, which is also equal to the rank of the projector, rank of the projector is same as the dimension on the subspace it projects. So delta n rho, these quantities is exactly sandwiched between the same quantities, exponent n of, you have now the quantum s of rho, but essentially the Shannon entropy of the eigenvalues. So plus delta, and this is lower bounded by, I'm writing this because this is a new thing, s of rho minus delta. And the third one becomes an operator inequality. That's why I'm going to write this red, because you have to keep note of this. There's an operator inequality. We'll prove all of them. We'll prove in the sense we'll just see that the proofs are straightforward. If I look at pi, if I sandwich my rho tensor n between the pi rho delta, this is at most 2 power minus n times s of rho minus delta times pi rho. So the operator is sandwiched. It's a very useful inequality because it's an operator equality. So it is proving all of the sequences at one shot in some sense. S of rho plus delta pi rho delta. So this is the operator inequality. So exactly those 3 properties hold, and you can do a lot of work with these 3 things. And then we'll also define conditional typical subspace, also just like the unconditional typical subspace. We do exactly like that. So that is why I kind of wanted you to kind of sweat through the homework so that this becomes easy now. Okay, questions, thoughts, comments. See, I have missed a couple of classes, and so it's let's see. Can I hold another class today? How many of you say? How many of you put a? I mean, it's totally fine if you say no. If I can hold another class today between 9:30 and 10:45, if you're okay, say, put a hands up. If you're not okay, put a hands down. And if you're not okay, totally fine. Between 9:30 and 10:45 today. So that is around, it's 6:45 now, 6:55 now. It's late, but if it's okay with you, let me know. I'll record this video, put the notes also. We'll have a few online classes because there's some constraint. No, okay, cool. I understand. And Tejas, you want to attend, right? Okay, I think Tejas is not wishes to, if I understand right, Tejas wishes to attend, but he can't make it. So so let's not do it. Let's try to do it tomorrow. I'll record this and post the, I'll actually stop the, yeah.